Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to talk about a property of the gamma function, and specifically we're going to prove this property that gamma of x plus 1 equals x times gamma of x for all positive x. Okay, so x can represent any positive number, not just integers and things like that. So recall the gamma function is defined to be gamma of x equals the integral from 0, let's go ahead and fix that, the integral from 0 to positive infinity of t to the x minus 1 e to the minus t dt. Okay, so what that means is that gamma of x plus 1 then is going to be the integral from 0 to positive infinity of t to the, so this is going to be x plus 1 minus, 1, because here we have x, and this is x plus 1, so we have x plus 1. Okay. But x plus 1 minus 1 simplifies to just plain old x, so we're just going to have that. And then we still have our e to the minus t dt right here. So what we want to do is show that this equals x times gamma of x. Okay, so this equality here is what we want to show. So I'm going to put WTS for want to show. All right, so this equality here is how this just follows from the definition of the gamma function. And this equality here is what we want to show. So let's go ahead and move on down to page 2 and start working on that. So we have the integral from 0 to plus infinity of t to the x e to the minus t dt. Now this is improper because we have the infinite limit, so I want to rewrite this as the limit as big B goes to positive infinity of the integral from 0 to b of t to the x e to the minus t dt. Now let's go ahead and integrate this by parts. So what we're going to say is u equals t to the x. So if this is u, then dv has to be everything else that's left over. So dv is e to the negative t dt, which means v equals negative e to the negative t. So what about du? Now we have to be very careful here because in this case t is our variable and x is our constant. So as far as the integral is concerned, x is just a plain old constant because we're integrating with respect to t, because we have the dt here. So t is the variable, x is the constant. So what we have is a variable raised to a constant. So for example, like t squared, a variable raised to a constant. If we want to take a derivative of that, that's going to be 2t, right? Well, here instead of t squared, we have t to the x, but it's the same principle because x is our constant in this case. So the derivative is just going to be xt to the x minus 1. And don't forget the dt, because we're actually dealing with differentials, because we have the du and the dt. So we're dealing with differentials here, so don't forget about the dt. Okay, so then now what we have is this is the limit as big B goes to positive infinity of, we're going to have a big old mess in square brackets here. So we're going to have uv, which is t to the x, negative e to the negative t, where t goes from 0 to big B. So remember, big B is representing this infinite limit up here. And then minus the integral from 0 to big B of v du. Okay, so remember the integration by parts formula says the integral of u dv equals uv minus the integral of v du. So this is exactly what we're using here. And continuing this, we have negative e to the negative t. Du is x t to the x minus 1 dt. And then we're going to close our big old square bracket. So just to make sure that we have everything here, let's go ahead and recap. This is u, this is our v, and this right here is v, and all of this stuff is du, including the dt. Okay, so everything checks out so far. So now let's go ahead and simplify this a little bit, and to give myself a little more room, I'm going to erase this right here. So we'll go ahead and get rid of that, part of that anyway. Okay, so this now equals the limit as big B goes to positive infinity of, so here we have negative t to the, let's go ahead and fix that, negative t to the x e to the negative t, where t goes from 0 to big B. Okay, so actually that should technically be inside the limit as well. So we'll close parentheses around that. And then here I'm going to push the limit into both of these. So this minus minus is going to give us a plus. So we're going to have plus the limit as big B goes to positive infinity of the integral from 0 to b of, let's say, x t to the x minus 1 e to the minus t dt. Okay, now we have two big terms here, this big term and this big term, and I want to focus on these terms one at a time. So let's go to page 3 and just focus on this term right here. So on page 3, we're going to look at the limit as big B goes to positive infinity of, so let me pull this minus sign out first. So we're going to have a minus sign out here. And then t to the x, e to the negative t, evaluated from t equals 0 to big B. So let's go ahead and fix that t equals big B. So this is going to be negative limit as b goes to positive infinity of, now we just evaluate at the top and then subtract evaluate at the bottom. So that's all that's going on here. So we're going to have b to the x times e to the negative b, okay? And then minus 0 to the x times e to the 0, okay? Because if t is 0, then negative 0 is just 0. So then what we have is negative limits as b goes to positive infinity of, now let's push the limit into both of these terms. So we have b to the x divided by e to the b, and then minus, well, what's going on here? Remember, x is restricted to be positive, okay? X is strictly greater than 0. So no matter what x is in this interval here, 0 to the x is always going to be 0, okay? So 0, e to the 0 is 1, 0 to the x is just 0, so this entire thing is just 0. So we just have minus 0, or really that'd be plus, I guess, because we have a minus sign here, a minus sign here. Not that it matters, it's all just 0, but we might as well be as accurate as we can. Now what happens here? So we're taking the limit as big B goes to infinity of b to the x divided by e to the b. So this might look really strange with the big B's, but just think about here, this is a power function, this is an exponential function. Exponential functions grow way, way more quickly than power functions. So this is really just a calculus 1 type limit here. So we can look at this and say, okay, it's a calculus 1 type limit, power function on top, exponential function on bottom. I know that exponential functions shoot off to infinity much, much more rapidly than power functions do. So it turns out that this entire limit is 0. And you can prove that rigorously using L'Hopital's rule and possibly some other different types of arguments, but we don't want to focus too much on that for this video because there's too much else going on. And this is sort of an earlier topic that you would usually talk about before covering the gamma function. So anyway, this entire limit is 0. Okay, so this whole thing here, this entire term is just 0. So that just leaves this term here. Let's go ahead and focus on that. And there's really not a whole lot to do with that. So we'll come over here, and we're going to focus on that second term. So that's the limit as big B goes to positive infinity of the integral from 0 to b of x t to the x minus 1, x times t to the x minus 1 e to the minus t dt. All right, now first of all, remember, as far as this integral is concerned, x is just a constant. So this x is basically just a constant multiple that we can pull out of the limit of the integral. So let's go ahead and do that. So we have limit as big B goes to positive infinity of x times the integral from 0 to b times t to the x minus 1 e to the minus t dt. And again, the reason we can do that is because this integral is with respect to t. T is the variable, x is a constant as far as this integral is concerned. So, and remember, it's okay to pull constants out of integrals, so we can pull the x out. And likewise, as far as this limit is concerned, x is a constant because the limit is just a limit in terms of b. Okay, the limit depends on b, has nothing to do with x. So we can pull x out of the limit as well. So we end up with x times the limit as b goes to positive infinity of the integral from 0 to b of t to the x minus 1 e to the minus t dt. And then finally we can say, okay, well, hey, what is this? Well, let me drop the limit notation and go back to this, 0 to positive infinity of t to the x minus 1 e to the minus t dt. Well, hey, does that look familiar? It probably does, because that is the gamma function evaluated at x. The integral from 0 to infinity, t to the x minus 1 e to the minus t dt. And then back here we have the integral from 0 to infinity, t to the x minus 1, e to the minus t dt. So that exactly is the gamma function. So right here, this is gamma of x, and it's being multiplied by this x right here. So as it turns out, this entire thing is equal to x times gamma of x. And that pretty much gives us exactly what we wanted to show. So if we go back to page 2 here, we see that this is equal to x times gamma of x. And remember, we started with this, and this is gamma of x plus 1. So we've just shown that gamma of x plus 1 equals 0 plus x gamma of x, which gives us exactly what we wanted. Okay, we've just shown that gamma of x plus 1 equals x times gamma of x, using mainly integration by parts and being careful with the limits on the integrals here. So this has been an explanation of this property of the gamma function. I hope you found this video helpful, and thank you for watching.